Yes, I think everyone see my screen now, right? Or at least I hope.
Yes.
Yes, yeah, we see it.
Okay, cool. Okay, so welcome everyone to Iclimabuilt webinar series, and today the topic is performance characterization of the building envelope, and today is part 2, which is related to testing from material to full-scale prototypes. We are honored to have our invited speakers from our partner from Polytechnic of Turin and ISE Fraunhofer. And during this webinar, it will be recorded, and you can write a question in the chat or wait until we have the Q&A session. And our first speaker is Fabio Favoino, and please welcome him.
Thank you, Nate. So I'm gonna share my screen. Right. Oops. Here it is. Okay, you should be able to see my presentation, right? Is it?
Yes.
Okay, so good afternoon, everyone. Thanks, Nate, for the introduction. So this afternoon we'll go over the second part of the webinar, which is related to performance characterization of the building envelope, and we will be mainly looking at testing of building envelope material from the material scale to full-scale prototype of building or facades. So just the contents of today. So there is a first introductory part about the Iclimabuilt project, and then we'll look into the material level thermohygrometric characterization in lab by Stefano Fantucci. And then we'll go over optical and solar characterization of materials and components in laboratory by Bruno Bueno from Fraunhofer. Then after a small Q&A, we'll look at a use of outdoor test facilities for characterization of dynamic building envelope systems with myself and Ginevra Castri. And then we'll go over the acoustic characterization from material scale to components and room scale with Louena, Shtrepi. So starting a little bit of context related to the project. So the Iclimabuilt in itself is an Horizon 2020 project, of which these seminars are part of. And the objective of the project is to provide an open innovation test beds, a consortium that is supporting the scale up of building envelope technologies from material, so TRL scale related, let's say 3-4 up to a TRL scale of 6-7. And we do so by providing a consortium of that provides different services, among the other advanced characterization for the material and the building envelope components, and on the other side, multi-scale simulation and so on. We do so within this project, looking at different application cases, starting from the pilot lines, which what we call the materials that are developed within the project and the related production facilities. These materials, these pilot lines, are then integrated within building envelope components, which are called within the project test cases, and we'll see some of them in this presentation. And then there is a scale of validation of this test case of the building envelope components in Living Lab. which is not part of this webinar. And aside from helping this internal development of material, so pilot runs and test cases, there is also a kind of external consortium validation, which is related to providing these services to external SMEs within an open call. Within the project, the work package 4, 5, and 6 are related to the performance characterization of material and building envelope components, while the work package 4 is related to the simulation, and the previous seminar was mainly looking providing example of the services in this domain. This seminar is mainly about work package 4, in which we look at the testing and the characterization of materials and building envelope components, so at these different scales, with lab tests, but also with the characterization in real climates by means of outdoor test facilities. And as well, we are working on digital twins of this experimental testing facility in real climates. And then another work package, which is not part of this seminar, is related to the final prototype evaluation demonstration in living labs. Within work package 5, so the main aim of this part of the project is to develop a consortium that is able to support material and building envelope development in terms of characterization of the material and the performance of the component. And also on the other side, to provide guidelines, methods for testing innovative materials and building envelope components. And so in this way, we demonstrate the capability of the consortium to provide these services internally and externally to the project. Just as a broad overview of, let's say, all the partners involved and the testing capabilities that they have, divided between the material level characterization and the building component level characterization. So on the material, we have a collaboration between 15 different testing partners, allowing a broad characterization of the properties of materials from different point of view, like from physical and mechanical properties, fire behavior, to chemical, optical properties, acoustic properties, and so on, with let's say more or less 60 to 70 different equipments that can be used. At the level instead of the building envelope component, you can see basically in this graph the different domain of characterization from thermal and solar, mass transport, daylight, durability, energy harvesting, acoustic, fire, structural, and so on. And we are a little bit like 9 testing partners institution. You can see some of the names below. Putting together overall like 60 different equipments. So at the level of the materials that are used within the then building envelope components that you will see, you can see a broad overview here from phase change material to thermoelectric generator, 3D printed components, cements, concrete-based wall materials, aerogel, and so on. A first part of the activity was dedicated to characterize all the material properties of these different materials used in the projects, with a total of 124 different properties across these different materials. For some of them, when we add high-performing material or a very particular one that were not covered by standard, we also organize round-robin and inter-laboratory campaigns, for example, for loose aerogel thermal conductivity or acoustic property of 3D printed acoustic panels and so on. And also that was performed a long campaign for durability aging tests across these different material, understanding what are the degradation of properties in time of this material. When these materials are assembled within a building envelope components, these building envelope components were not very defined at the beginning of the project. So in order to define a testing protocol for these building envelope components, we developed a testing plan tool in which we were able to summarize the general characteristic of the building envelope component, the performance specification defining what are the main functionalities and aims of the component and what are the target key performance indicators and benchmark, so that we are able to define a testing plan, a preliminary testing plan. And this tool was automated and put into an online database, so to be able to interface with the testing plan in itself. Being able to, let's say, cover and manage the testing of these different test cases that you see, from, let's say, an example of smart window to BIPV components, to opaque, lightweight, prefabricated components, to 3D printed components for indoor environmental quality. Which is, so this scheme gives a broader picture of the different kind of building envelope components or test cases that were characterized over the different domain of investigation. So this gives an overview of all the tests that were done. And of the seminar of today, we'll be mainly looking at the some examples of thermal, optical, solar characterization and acoustic characterization of some of these components, just to show you also what we did within the projects. Most of the activity were done in POLITO, in the research group I'm working with, which is the Technology, Energy, Building and Environment research group. We used quite different labs. So starting from the, and you can see in this slide both, so all the labs that are involved in this kind of presentation, including the one of Fraunhofer, related to the solar and optical characterization. And so the one in green are the ones that we are actually showing as example in this presentation, which are laboratories that are spanning from an application to low tier AL, so lab scale, few centimeters, up to full scale test facility for outdoor test facilities. So this is a brief introduction of the context of this seminar. And I will leave here the stage to my colleague, Professor Fantucci. So I'll stop sharing so he can share his screen. So Stefano, floor is yours.
Thank you, Fabio, for your brief introduction. I try to show my screen, and just let me know if you look the screen properly.
Yeah, we can see it.
Okay. Okay, well, the presentation of today will be related to the thermal and hygrometric characterization of materials. I will specify that basically I will talk mainly about advanced and innovative materials for building envelope components, and all the properties are basically in this presentation presented as to be assessed in laboratory condition. Regarding the contents of this presentation, I will present some case studies. One will be related to superinsulating materials. The second is about phase change materials, and the third one about the moisture buffering materials, in order to try to give a general overview of the main challenges related to the characterization of advanced materials for building envelope. And basically, to start this topic, I have to say that advanced building envelope materials have faced a rapid diffusion in the last few years, especially for the energy retrofit of existing buildings, but also when we want to go towards the nearly zero energy building target. However, their practical application is nowadays still limited because there are some open issues that has to be solved. First of all, there are a kind of inadequacy of the standard test protocols that does not allow to characterize directly the material properties, or does not allow to consider the material properties that we can determine with these traditional testing protocols to be directly turned in the building envelope component overall or equivalent properties. Then there is also the need to reduce the gap between the expected and the actual performance. And for sure, for the practitioners and technicians, there is the need of simplified thermal performance metric that need to be still defined. Talking about these materials, I will start with the category of the super-insulating materials. Generally, super-insulating materials can be considered all the materials having a thermal conductivity that is lower than the still air thermal conductivity. So in this category falls all the nanoporous materials, such as the aerogels, but also evacuated materials, such as the vacuum insulation panels. I will start my presentation by talking about the activity we have done on the aerogels, and especially the activities that are related to the characterization phase of the Iclimabuilt project. So one of the pilot line that was developed in the Iclimabuilt project was this hydrophilic granular silica aerogel. And silica aerogel is basically a material that is characterized by a very low density and a nanoporosity. So the typical pore diameter is between 5 to 70 nanometers. And it has super insulation properties with a thermal conductivity between 13 to 25 milliwatt per meter Kelvin. They represent for sure a promising solution as a thermal insulating materials and can be frequently embedded within building components in their granular form. So for this reason, we start our characterization of thermal conductivity by trying to measure the thermal conductivity in two different conditions. The dry conditions by drying the material in a ventilated oven, and a second characterization were done considering the moist condition. So when the material is generally applied, the temperature and relative humidity can be in the range of 23 Celsius degree and 50% relative humidity. So that are basically the actual condition in which the material is generally exposed. So in order to try to understand the thermal conductivity in these two conditions, we perform tests in the heat flow meter apparatus. Then the main challenge we find out is that when we try to test microporous or porous materials that are hydrophilic, such as in this case, this kind of aerogel, there is a problem of moisture redistribution while we perform the test. So the general assumption for which we have a uniform or a homogeneous thermal conductivity over all the specimen is generally not valid in this condition, because this redistribution of moistures determine basically different layers of materials having different thermal conductivity. And this is basically because having different moisture content generate a different thermal conductivity, because thermal conductivity is non-linearly dependent from the moisture content. So to perform this test, we basically modify the standard test protocol by applying additional temperature and humidity sensors in the specimen, and we try to measure the thermal conductivity. So what we find out basically prove our initial assumption, our initial suspect, that in fact we have a moisture redistribution. In fact, as you can see on your left side, the plot with the measurement of the dry aerogel samples show basically a close value of thermal conductivity between the upper side and the lower side, so with a minimal difference of about 8% between those two thermal conductivities. While when we move to the moist aerogel samples, we have quite an important differences between the the lower part and the upper part. And in fact, basically the upper side of the aerosol samples has a very high relative humidity, so high water vapor pressure level that increase the moisture content in the material and jeopardize potentially the properties of the material itself. And in this case, as you can see, basically we have an important difference between the bottom part and the upper part of our samples that can be up to 30–34%. This is something which is very important to take into account when we intend to characterize porous materials that are in moist condition. The second materials we work in are vacuum insulation panels. These kind of materials are basically microporous materials that are evacuated, and the evacuation allow basically to neglect the convection and the gaseous conduction contribution inside the porous matrix. So what remains is just the solid contribution and the radiative contribution inside the micropores that basically allow to achieve very low value of thermal conductivity between 2 and 8 milliwatt per meter Kelvin, which is 5 to 10, 15 times lower than a conventional thermal insulating materials. So what we find out is that for this kind of material, special attention has to be taken when we want to perform accurate tests for the thermal conductivity, because generally the instruments are built up to work with materials that have a conventional thermal conductivity. But what happens when we have a thermal conductivity that is an order of magnitude lower compared to the traditional materials? Then there is an important effect of the temperature on the thermal conductivity. And then the third effect is related to the thermal bridging effect, which impact basically not the material property itself, but mainly the material when they are applied or coupled together to create a building component or a multi-layer building component. So first of all, to perform accurate measurement on vacuum insulation panels, to fulfill the standard requirements, we need to have an acceptable heat flux that allows us to have a measurement uncertainty below 3% by using the heat flow meter apparatus. So we find out that to fulfill this kind of requirements, the general temperature difference between the two plates of the instruments, the upper and the lower one, that might be in the range of 10 to 20 Celsius degree of temperature difference, basically is not always valid. So when we are facing a material that have a thermal conductivity that is very low and a very low thermal resistance, what we find out is that there is the need to increase quite a lot the temperature difference between the two plates in order to achieve and to fulfill the requirement of the measurement standards. And in some cases, when we have a very thick thermal insulation layer and very low thermal conductivity, it will be quite hard to assess the thermal conductivity by using this kind of methodology. But in any case, the temperature difference between 10 to 20 can be, on general, like more than 20 Celsius degree in order to have an accurate test results. The second effect we find out it's important for this kind of material is the temperature effect. So in general, on traditional materials, the temperature in the range of the typical temperature in which a building operates does not determine a significant increase of the thermal conductivity, or the relationship is mainly a linear relationship. What we find out is that when we move from the left side on a non-evacuated core material, we have an increase of the thermal conductivity between -7 degrees C to 55 Celsius degrees C of about 8%, which is basically negligible. But when we move to an evacuated material that you can see on the plot on your right side, first, there is a nonlinear relationship of the temperature and the thermal conductivity. And secondly, for sure, the increase is about 50% in the thermal conductivity itself. This is quite important because it turns us to some consideration when we have to apply this material in buildings. Because a typical thermal conductivity measured at 10 Celsius degree or at 23 Celsius degrees C, it's not always valid. For instance, if we operate with building components that are quite exposed to the solar radiation, or if the material is used for the insulation of thermal storage tank or district heating pipeline, the typical thermal conductivity measured at that specific condition cannot be directly used. So this suggests that there is for sure the need of having adequate thermal conductivity condition measurements according to the specific use of the material in the building. The third aspect is related to the thermal bridging effect. So when we move to the material to the component scale, generally vacuum insulated panel cannot be directly applied to the wall components alone. They generally need some construction joints that determine a thermal bridge. So these thermal bridges can be assessed by the heat flow meter apparatus, and we use these measurements for validate simulation model made on finite element or finite difference method. And we use this simulation model to try to understand what can be the impact of the thermal bridging when we move from the material scale to the component scale. And in fact, we find out that in a multi-layer wall component, we might expect to have quite a not negligible increase of the thermal conductivity. And also when we move from the component scale to the building scale, we can see that we have a non-negligible increase in the building transmission heat transfer coefficient, depending for sure on the building shape and on the type of joint that is used to couple vacuum insulated panels. But for sure, this kind of influence is something that has to be taken into account. Then, regarding phase change material, we have to say that most of the phase change material that are present on the market are generally macro-encapsulated in order to be applied in a building envelope. So there is nowadays the issue that typically the product data of the PCM, which is phase change materials, are data that are related to the material itself. This kind of measurements are generally performed by using the DSC method, which is the differential scanning calorimeter method, that is done on few milligrams of or few grams of bulk PCMs. Unfortunately, when we try to apply this material inside a macro-encapsulated component, they can be plastic case or metallic case, we have basically a complex behavior that is not fully represented by a test that is done in a DSC. That's why in the last few years, a new standard procedures has been developed, which is basically attested by the ASTM C1784 standard, which is an American standard that allowed to use the dynamic heat flow meter apparatus to measure the dynamic properties of the phase change materials, such as the accumulated enthalpy distribution and the specific heat at different temperature. So what is important basically is that we can move from the material property to the material when it is sandwiched or it is embedded inside a component. What we find out is that for sure there are still some testing limitations. For instance, one effect that is basically something we have to take into account both for the SC method and also for the heat flow meter method is that there is an effect or the quantity of the material that is used basically affect the performance and the properties of the material. So it is something that we can basically neglect as an issue when we move from the material to the component by using the dynamic heat flow meter apparatus. But another issue that still remains open is related to the effect of the test speed, because generally phase change material are exposed to a dynamics that is the typical dynamics of a building, depending on the typical usage of the building. So we try to perform some tests, and we try to compare the results of the heat capacity and also of the thermal conductivity of different macroencapsulated phase change materials. So we find out that for both the thermal conductivity and for the heat capacity, basically the data on the material itself that are measured by using the DSC or either the free layer calorimeter are not fully representative of what happened in a complex shape that is the one of the microencapsulated phase change materials. Unfortunately, technicians and practitioners that have to simulate this material with building envelope or with building thermal energy simulation tools need to have equivalent data to adequately perform this kind of simulation. So there is the need of performing the experimental assessment on the full component and not just on the material itself. Here you can see some example of the materials or the phase change materials embedded in multi-layer components, and how it's possible, for instance, to replicate the typical sinusoidal condition that happen in a building envelope when it is exposed to the external boundary or internal boundary conditions. And we find out that it is possible basically to perform this kind of sinusoidal response measurement procedures by soliciting one side of our samples and by measuring the response on the opposite side. We try to perform this kind of test also in materials and components that are developed in the framework of the Iclimabuilt project. For instance, in the TC6, the test case 6, a sandwich component embedding PCM has been developed. And for instance, we measure the full scale, basically the overall dynamic properties and thermal inertia related properties to the components with and without the phase change materials. And we find out that with this methodology, it is possible basically to determine an equivalent periodic thermal transmittance and an equivalent time shift of the heat wave that can be for sure improved by the use of phase change materials. Then the last materials that I present are basically the moisture buffering materials. Moisture buffering is a way to control the fluctuation of relative humidity in indoor spaces by trying to shave the relative humidity peak levels, which are generally responsible of discomfort condition in the building and poor indoor air quality. The moisture buffering indicates basically the amount of moisture that is transported in or out of the material per open surface area during a certain period of time when it is subject to a variation of relative humidity on the surrounding environment. So this is, as you can see in the top left plot, the typical climatic chamber test that can be done on materials to measure the moisture buffering. And basically the principle is to create cycle of very high relative humidity followed by cycles of very low relative humidity in order to appreciate the moisture storage capacity and moisture storage release of the material. So what we find out is that these kind of tests are generally something that allow to assess the typical moisture buffer value of materials. But when we deal with complex components, we cannot refer to the property of the material itself, but we need to use a different key performance indicator that in this case is the practical moisture buffer value. As you can see in this plot, for instance, this is a 3D printed component that are printed by using clay. The moisture buffering material of solid clay is between 2 and 3 grams per square meter per percentage change of relative humidity. But if we 3D print the component, we maximize the surface that exchange with the boundaries, with the indoor air, basically, and we might expect to have up to 5 times higher moisture buffering value. So this is quite interesting, but this is also open a number of questions about the reliability of the typical testing procedures that has a fixed condition of 8 hours at very high temperature, followed by 16 hours at very low temperature. That can be very low relative humidity. That can be acceptable for some final use of buildings, but it is not for sure representative of all the typical usage of buildings. For instance, we might have the need of assessing the moisture buffering with different timing and different solicitation, basically to assess different kind of usage of the building depending on the occupation schedule. This is quite important, especially if we want to appreciate materials that present complex change, complex shapes, especially in the surface, because we expect that this kind of material might have also a faster response to the outdoor solicitation. And this is a way for sure to accurately and to adequately estimate the moisture buffering of these complex materials. So to conclude, advanced building envelope materials and components could potentially represent a viable way to improve the energy efficiency of buildings, for sure. But however, to be largely adopted in the building sectors, we have the need to reduce the gap between expected and actual performance when these materials are implemented in buildings. The simulation models and tools should consider the complex thermal behavior that need to be measured in an adequate way by using laboratory testing. And specific ad hoc experimental procedure and protocols need to be developed. This should be coherent with the intended end use in the building. That's all from my side, and I'm open to answer all your questions. Thank you for your attention.
Okay, I think we can move to Bruno, and then we have a Q&A after its part. So Bruno, if you want to share directly your presentation, thanks.
Do you see it well?
Yes, thank you.
Thank you. Okay, so now it's my turn. I am Bruno Bueno. I work at Fraunhofer Institute for Solar Energy Systems in Freiburg in Germany. I'm leading a group which is called Solar Building Envelopes, and within the group we have an accredited laboratory for the optical and thermal characterization of facade materials and components. So today I'm gonna present in 10 minutes some of the approaches we take in the lab to characterize the optical performance of materials and components. The scope of the presentation covers both semi-transparent facade components, so basically fenestration systems, and opaque facade components with a focus on BIPV, built-in integrated photovoltaics. So here I show some examples of the type of systems we can characterize in our lab. This would be a solar control glazing unit with interior roller blinds. These are scent blinds, a special shading device which is angular selective and glare free. We developed that at the institute. This is an integration of colored PV in an historical building in Germany, and this is semi-transparent BIPV installation in our facilities in Freiburg. So we can characterize optical properties from facade components. And the definitions of optical properties can be found in this European standard 14500. It is useful to differentiate between two domains of optical properties: the spatial domain or angular domain. There we can measure the normal transmission or reflection. Normal means normal to the sample plane, and then again normal would be the outgoing light direction that we measure. We can also measure normal diffuse reflection and transmission, and then the sum of both of them, normal and diffuse, would be the hemispherical optical properties. In addition to that, and for angular selective shading devices, it is also useful to measure the cutoff angle because you can get a higher class of performance if you have a low cutoff angle in your shading device. The second domain is the spectral one. We can measure spectrally resolved transmittance and reflectance, and from this spectral distribution we can calculate the broadband solar transmittance or reflectance, and also the broadband visible transmittance and reflectance, which, as you know, only includes the visible part of the spectrum. And in addition to that, we have to weight the spectral distribution with the sensitivity of the human eye to the spectrum of light. So how can we measure the angular dependent transmittance and reflectance over the solar range, both spectral distribution and broadband properties? We do that with the help of integrating spheres and spectrometers. We can have integrating spheres of different sizes, and they are all suited for different purposes. The measurement principle is simple. We place, for the case of transmission measurement, we place a sample in front of the sphere in a port. We illuminate the sample with a light source, and then the scatter light enters the sphere. The sphere is coated with a very reflective material, so at some point all the scatter light reaches a spectrometer. So then we can calculate the spectrum of the normal hemispherical transmittance of the sample material. If we would open a port here on the specular direction, according to the incoming light direction, then we allow the specular component of the scatter light to leave the sphere, and we would be measuring the normal diffuse transmittance of the material. Most commercial spectrometers and integrating spheres only allow the measurement of the normal properties, normal incident light. We have a setup at the institute where we can rotate the sphere. It's a large sphere, and then we can measure the angular dependent transmittance and reflectance. Now, as you know, the performance of facade components is dynamic, so it changes according to the time of the day and the day of the year. So the standard properties, normal, diffuse, normal hemispherical, transmittance and reflectance are not enough to evaluate the dynamic performance of facade components. So we need bi-directional optical properties and a good and a well-defined magnitude. To do that is called bidirectional scattering distribution functions, which includes already a transmission component and reflection component, and describes the spatial distribution of light scatter for different incoming directions of light. Just to explain a little bit more this concept of BSDF, here we would have a plane which represents the sample, and then we can discretize the hemisphere of incoming light directions in a number of solid angles. We discretize the hemisphere of outgoing light directions for a number of solid angles, and then for each combination of solid angles in the incoming hemispheres and solid angles in the outgoing hemisphere, we can have a BSDF value which has units of inverse stereo radiance, but it can be translated to a transmittance or a reflectance value if we take into account the solid angle. So at the end, we have large data sets for all combinations of incoming and outgoing angles, and for reflections and transmissions. These data sets can also be represented in matrix form, and then we can use algebraic methods to manipulate them. So there are different measurement setups to characterize BSDFs. The one we have at the Institute is a 3D scanning photogoniometer. Here we have a sample in a sample holder, and we illuminate the sample with a light source again. And then we have a robotic arm, which is able to rotate around the sample following the surface of a sphere. So it can measure transmittance when the sensor is behind the sample, and it can measure reflectance when the sensor is in front of the sample, and it will do that for different positions of the sensors. So we would be measuring light intensity for different outgoing light directions. To change the incoming light directions, we can rotate the sample like this, or also relative to another axis. BSDFs have different applications. The most straightforward is fenestration systems and shading devices, but we use also BSDFs to characterize certain properties of BIPV, and one of them is the anti-glare behavior of PV modules. So here in the picture, we see the BIPV installation of the Iclimabuilt project in Manresa in Spain, and we can compare the color modules we developed in the project, for which we need already a structured glazing, and therefore it has automatically anti-glare properties. And here we see another module with a fully specular front glass, so we can see the glare effect. The glare is a problem for BIPV. We want to increase the installed capacity of PV in cities So we will install PV on the facade, and these are glazed surfaces and can cause glare problems. And there are different technological approaches to mitigate the problem. The most common ones are anti-glare coating and glass structuring. So we are working on methods to evaluate, to quantify the anti-glare properties of these different technological approaches. So here I have some examples on how do we use PSDF for this purpose. So on the left-hand side, we have a extraction of BRDF. So in this case, only reflection for clear glass. So we see there is a very bright peak, a very small peak, which reaches up to 600 inverse stereo radians. So this is already a very glary situation. If we apply as light structuring on the front glass of PV, we already see a scattering of the reflected light, and the BRDF values we reach is around 10 inverse stereo radians. This is still a glary material. If we move to a macroscopic structure, such as pyramids, we can go down to 0.5 inverse stereo radians. This is already an interesting range. And then if we look for more advanced technologies like chemical acid or laser structuring, then we can go down to 0.1 inverse stereo radians, and this is already a glare protection device. So this is what I wanted to tell you today. We can answer questions at the end of the seminar. Thank you.
Okay, Fabio. Yes.
Yeah, okay. We thought about a first small Q&A session here, just to break a little bit between the two parts of the seminar. So yeah, if you have any question for this, let's say first part of the seminar, please drop it in the chat, or feel free to raise your hand, and we'll give you the mic.
So, Bueno.
Yeah.
Bruno.
So I have a question for the for Stefano. When you talked about vacuum insulation, you said you could suppress the convection heat transfer. What about the radiation heat transfer? It would be relatively easy to apply selective coatings to the material. Is this a common thing to do?
Generally, thank you, Bruno, for this question. Generally, to suppress the radiative heat transfer contribution, there are some opacifier inside the microporous structure that are used. So we can also basically consider suppressed the radiative heat transfer contribution. Nonetheless, since there are basically a microporous structure, so a huge number of pores, the main driver of the radiative transfer contribution is the temperature difference across each pores. And since this temperature difference is very low, this also reduce a lot the radiative transfer contribution in the porous media. But you are right. There are some opacifiers that are used also to reduce the radiativity exchange, that reduce the thermal emissivity, basically.
So anyone else, do you have any question? I also have a small question about regarding to the standard. For Stefano, I saw that you had used ASTM standard, so I would like to ask about the EN standard. Do you know that we don't have it at all, or we will kind of work into the EN standard towards this kind of test on the, yeah.
Well, Lane, thank you for this question. Basically, it is quite a recent standard, the American one. So the ASTM standard has been published in 2020, if I well remember. So it is quite recent, and there is not actually an European standard that is used. So there is no European standard. The only European standard or international standard for phase change materials is related to the differential scanning calorimeter approach, which is for sure reliable when we deal with a small quantity of material and when we want to assess the thermal conductivity of the material itself. But when we move from the material to the small scale component, for sure it's something that cannot be tested in such a way.
Okay. There is some comment. There is exist battery passports. Is it possible that there exist or in the near future there are passports for material and full-scale building components? From Elena Gomez, maybe I can allow you to ask directly. I mean, I will activate your micro. Yeah, now can you speak or not? You are in mute, I think. Oh. Okay, there's a question in the chat, so probably you can also read it. Oh, okay, but we are kind of running out of time as well. Probably, I think maybe this can be in the last session of Q&A if we have time. So I think we probably go on with the next session. What do you think, Fabio? Because we still have 2 presentations left.
Yeah, I think we can go on. Thanks.
Okay.
Thanks, Nate. So the second part of this seminar is related to the use of outdoor test facilities for thermal performance characterization of building envelope systems. And I will present this together with my co-presenter, Ginevra. Well, the premise is that building envelope components are, let's say, starting to be more and more a multifunctional element. So we're not just looking at providing thermal insulation within the building. If we look at the thermal performance, but as you can see from also the presentation of Bruno, they are able to impact largely with a very complex, let's say, spatial and spectral discretization the indoor environment. But they can also maybe preheat fresh air before it goes into the indoor space, and control surface temperature, condensation risk, and many more. So in a way, they start having properties that are hardly described, that can be hardly described by let's say one simple overall integral metric. They are largely dependent on the use of the operation of the building envelope component itself, on the boundary condition, as you can see, and also for maybe moisture buffering material or VAP panels. So there is more and more the need for lifelike performance characterization and validation rather than just a test lab, or at least test lab that are thought in a way to represent lifelike condition. Just to give you an example, whenever we use the in a potentially double skin facades, the preheated air and the cavity ventilation in order to preheat the air to then admit it in the indoor environment, or to bring it back outdoor in summer, for example. This largely affects the temperature of that air largely affects the total solar gain coefficients of the double skin facade. So it makes it very, very dependent, the G value and the U value of that facade, largely dependent on the boundary condition and the operation itself of the ventilation within the cavity. So traditionally, we always had two kind of approaches to test the performance of building envelopes, either going into a lab characterization that's inherently more accurate because you're controlling better all the influential parameters, but is usually set in steady state boundary condition or predefines dynamic sequences. And within this test facility, just one or maybe more outdoor weather conditions are somehow mimicked, but it's difficult to mimic them. But in a way, this is not fully reproducing the stochastic processes of the outdoor real climates. When we go real buildings instead, it's very difficult to do a characterization test in which we are able to isolate a single variables because of the main influential factors, either externally or internally, that you have in a real building. So the data also that you take from different experiments are hardly comparable. And also the kind of measurements apparatus that you use and the way you're able to control the experiments doesn't allow to have very, let's say, reliable measurements in itself. So in between these two scales, there is the use of outdoor test facilities, which are in a way not antagonists, of course, to one of these two scales, so lab or real building, but in a way is complementary to the kind of test that can be done in a lab or in a real building. So in a way, in outdoor test facilities, you are able to test the performance of full-scale mock-up of building envelope components in dynamic real climatic condition with an indoor environment that is very representative of what could be an actual indoor space like an office space. And normally these facilities are used to assess the representativeness of what is the performance characterized on the lab scale, but also to provide data to empirically validate models then that are used for example, building energy simulation tools, but also to do a like-for-like comparison with benchmark technologies, testing two or more technologies at the same time within two comparative test cells. And you do so by having on the other side a very high quality measurement apparatus and in which you are able to control environmental condition in a very accurate way. On the other side, they are quite time consuming and resource intensive measurements, and they take usually more than one season in order to capture the actual operation in real climates. And there are no actual standards to perform these measurements. In the years, depending on the kind of facade application, different performance metrics were introduced in order to characterize the performance of specific technologies. For example, here you have an overview of characterization tests that we'll see a little bit more in detail related to facades that are using somehow the ventilation within a cavity. That are either on one side described as a kind of efficiency, or on the other side they measure the net energy fluxes going through the component, positive or negative, in representative climate conditions. So the common characteristic of all these metrics that are these are not a physical parameter like Q value or G value, but they rather represent a synthetic KPI towards a certain objective. For example, the ability to reduce solar loads or to preheat the air before it goes into the environment. And in general, they are expressed as an efficiency, so a useful effect divided by the total expenditure of energy or the availability of the free energy that we want to exploit. And these metrics need to be somehow normalized with respect to the boundary condition in which they are calculated. So temperature, amount of solar radiation, solar geometry, and so on, in order to be comparable across different boundary conditions and between different technologies. And these metrics are usually calculated as a distribution over a large set of data, which are hourly data or daily data that can be also looked for the whole season or in specific representative condition like typical peak or average days in different season. So this is a little bit the let's say overview related to the need, the requirements, and why going to a test in an outdoor test facility, and a little bit the nature of a kind of metrics that can be assessed compared to usual metrics that instead are assessed in lab condition. And I will leave you with my colleague Ginevra Castri that will present you an application example of a test of heat harvesting window, namely test case 1 in Iclimabuilt, by using an outdoor test facility, so we can go a little bit deeper into also the metrics and what can be done.
Thank you, Fabio. I will share my screen. Okay. Okay, so linking to what Professor Favoino just presented, today I would like to explain to you how we characterized from an experimental point of view what we call test case 1 in the Iclimabuilt project, which is an advanced fenestration system composed of a double skin facade linked to a PCM to air heat exchanger. As Professor Fabio just said, we are interested in characterizing such a system because we are moving towards a system which has to be dynamic, which has to have a multi-objective aim. In this case, with this system, we are not just talking about a fenestration system, but is a system which is able to harvest the solar radiation and also modulate the ventilation of fresh air between outdoor air and the indoor environment. So, looking more in depth to our full-scale mock-up, here to the right we can see a picture of our test case 1, or our double skin facade. This double skin facade is installed in our testing facility, which is located in Polytechnic of Torino, in the roof of our department, and this is exposed to south. It is composed of 2 main parts, as I just said, which are the double skin part and the PCM to air heat exchanger. The double skin is a mechanically ventilated one, which has 2 different openings, one in the bottom part and one in the upper part. So going a little bit more in depth into the system, the double skin is composed of two different chambers. The chamber next to the indoor environment is filled with argon and air. So it's an insulating chamber, while the chamber next to the outdoor environment is the mechanically ventilated one, but we are talking about a thin cavity, thin double skin cavity, about 30 millimeters. The coatings that the glazing stratigraphy present were designed in order to harvest more solar radiation possible in order to preheat the air inside the ventilated cavity. We have an omniphobic coating on the outdoor glass, which prevent like the self-cleaning properties of the glass. Inside we have a pyrolytic low emission coating and a selective coating on the other pane glass. For what concerns the PCM to air heat exchanger, in our case we have two different PCM to air heat exchanger. Each of these is made of 5 different plates of PCM, which is encapsulated in aluminum plates. And what's really important is that we have mechanical fans that let us decide the operational ventilation mode that the facade can have in order to make the system more flexible for the climate of application. All the results that I'm going to present to you refer to a PCM melting temperature of 21 degrees. So looking at the operational mode for this kind of facade, we have the supply air mode, which is used in cold climate or during winter, in which we take air from outdoor. The air goes through the cavity and is preheated by the solar radiation, and then is forced to go, thanks to the fan in the upper part, through the PCM to air heat exchanger. Then we have the outdoor air curtain mode, which is used during summer period or hot climates, in which we take air from outdoor, the air is preheated and then is expelled from the other opening. In this way, we are avoiding some heat to enter the environment, but while doing that, we are still able to provide the indoor environment with fresh air thanks to the structure that we have here with the fans and the PCM to air heat exchanger. Lastly, we have the thermal buffer mode, in which the fan in the bottom part are off, meaning that the double skin part is working as a triple glazing unit, but while having a static component, we are still able to guarantee to the indoor environment air changes thanks to the fans in the upper part and the PCM to air heat exchanger. So, moving to the experimental setup, as Professor Fabio just said, monitoring this kind of system requires a very huge experimental setup, experimental sensor. The twin test facility, in the twin test facility, we have a local climate station in order to monitor real-time boundary condition. We have an ACVC indoor system in order to maintain the set point temperature, which for us, for winter, are equal to 20 degrees, while for summer period is 26 degrees. And then we have all the other sensors for what concern the fenestration system, meaning that we have sensor not only outdoor and indoor the fenestration system, but also inside. And when I say sensor, I mean temperature sensor, heat flux sensor, but also different of pressure in order to capture and understand the effect of the airflow on the glass panes. Of course, the same happens when go to the PCM to air heat exchanger, in which we have other sensors to monitor the temperature of the plates, the air temperature, air velocity, and pressure difference. So all the data that I will show to you are post-processed from the experimental data monitored with this setup. So to evaluate the performances of this system and the behavior of this system, the methodology that we applied were to calculate, to post-process some KPIs. As Professor Favoino said, let's say that static KPI like the U value, the solar transmittance, and the G value, when it comes to this kind of system, let's say they are not enough, because of course the behavior changes a lot because we have air which is flowing inside. So of course we're gonna see the U value calculated, which is the thermal insulation of the component, the solar transmission through the window, the G value, which is the ratio between the net thermal energy entering through the window divided by the solar irradiance on the window. And then we have other KPIs which are the dynamic one, which, let's say, they refer to also the ventilation operational mode. So, for example, for the operational mode of supply air, we will define a pre-heating efficiency. For the operation of outdoor air curtain, we will define a dynamic insulation efficiency. And for the operation of thermal buffer, we will define a thermal buffer efficiency. This efficiency so refers to the double skin component. We have another efficiency, which is the efficiency of the PCM, which refers to the PCM to air heat exchanger level. And then we have developed another efficiency which refers to the entire system, so the test case 1, double skin facade plus PCM to air heat exchanger. And then we also did a comparison considering a triple glazing unit with the same thermal and optical properties of the case study. When it comes to experimental measurement, we developed an experimental plan in order to make sure to capture all the behavior that the system can have. We started in September approximately, so we have summer, mid-season, and winter. And our aim was to change ventilation strategies, the set point temperature, but also mass flow rate elaborated from the facade, in order to define the KPIs I was talking about before for all these different periods. Moreover, we selected some representative days in order to make them representative. So starting from the U value, as I said, the ventilation inside the cavity influenced the U value calculation a lot. So let's say that the most valuable calculation is in thermal buffer mode, because, as I said, is the mode in which the double skin facade behave like a triple glazing unit. We calculated the U value with different methods. We considered and filtered the data using just night data, so without solar radiation, but also the data that weren't close to the sunset, in order not to take into account the inertia of the entire system. And we calculated it in winter to reduce the experimental error. We can see that compared to the value simulated, calculated with the software window, which was 1.15 watt over square meter Kelvin, the experimental value that we calculated was approximately 1.25 watt over square meter Kelvin. So it's quite close to the simulated one, but it's not equal to this. Regarding the tau sol, so the solar transmittance of the system, what we did was to calculate it considering only daytime hours. It was calculated also by changing the incidence angle in function of the period, and the data we obtained were quite close to the data simulated, again with the software window. In fact, with the simulation, we obtained the value of 0.16, 0.18, while with experimental data, we obtained 0.15, 0.18. When it comes to the G value, what we can see here, for example, are the yellow line, which represent the simulated tau sol, while the gray line represents the simulated G value. Theoretically, the G value should not go lower than the yellow line, so the tau sol simulated. So let's say that all the data that were below this line means that the experimental error is too big. So the value of the G value should be between this line and the gray line. The simulated G value that we obtained was 0.35, while the experimental G value was between 0.16 and 0.21. This means that the entire system, so the fact that we have a ventilated facade, ventilated double skin, influence a lot the G value by decreasing it. Moving to the dynamic KPI regarding the supply air mode, we calculated the pre-heating efficiency. The operating efficiency is an efficiency which gives an information about how well we are creating the air inside the cavity. Let's say that the way to read this graph is that we want operating efficiency closer to 1, because it means that we are introducing air at the PCM2 heat exchanger, if we refer to the double skin, or to the indoor environment, if we refer to the entire system, closer to the set point temperature, which for winter was 20 degrees. As we can see here, the green line is the case in which we have just the double skin, so it's with the temperature at the exit point of the double skin, while the red line is the exit point after the PCM2 heat exchanger. When we introduce, when we have operating efficiency which are too high, like 1.5 or 2, it means that we are introducing air at a high temperature, which is not very good because, first of all, we could create thermal discomfort, and also because we don't need so high temperature. With the use of a PCM2 heat exchanger, it is shown how it is possible to decrease this temperature, because the PCM charge by subtracting some air, in order to have values which are closer to 1. The same behavior can be seen when looking at the temperature at the exit point of the double skin, if we look at the green line, and the PCM2 heat exchanger if we look at the red line. Let's say that on average, the results that we obtained for the entire system are 0.51, which is very, very good. For what concerns thermal buffer efficiency, it gives an information about the reduction of the transmission losses. If we have a value of thermal buffer efficiency between 0 and 1, we are reducing them, while if we have a thermal buffer efficiency higher than 1, we have its gains. What we obtained for the thermal buffer period are thermal buffer efficiency between 0.5 and 0.7 on average, which again are very good value. Here, again, referring to the supply air mode, we can see the energy and air temperature trend for a representative day. This graph in the upper part of the slide is very interesting because it gives an information of how the entire system is behaving. So looking, for example, at the black line, here we can see the outdoor temperature trend, meaning that this is the air temperature entering the cavity. Then when there is solar radiation, which is the orange area, the system is able to preheat the air which is entering the cavity from the black line, so from the outdoor air temperature, to the red line, which is the temperature of the air exiting the cavity. Of course, the behavior of just the cavity follow the behavior of the solar radiation. So when we have peak of solar radiation, we have peak of temperature. When we add the PCM2 heat exchanger, so the air which has the red trend goes inside the PCM2 heat exchanger, it follows the light blue line, meaning that the temperature follow again the same trend, and it's near the set point temperature of 20 degrees. But when there is no more solar radiation, so for example here after 3 p.m., the PCM is able to discharge and heat up the air which is exiting the cavity, as we can see, at a lower temperature, up to closer to the set point temperature, even until night hours, meaning that the use of a PCM2 heat exchanger is working very well for the entire system. Here we can see regarding
Ginevra, could you please wrap up a little bit?
Yes.
Yes,
sure. Yes, sorry. Here we can see the results for the comparison between our results to what we would obtain if we had a triple glazing unit with the same optical and thermal characteristic. And what we can see is that we decrease by half the ventilation losses. Again, meaning that the system is working very good. Here we can see the dynamic insulation efficiency, which refer to the outdoor curtain mode, in which we obtained results. Again, we want results very close to 1, because it means that we are expelling air, we are reducing the heat gain in the indoor environment, and the results that we obtained are between 0.7 and 0.9 on average. Here we can see the typical day, again, but for summer, so in outdoor curtain mode, in which the behavior is it's like the opposite compared to the winter period, because when we have high solar radiation, so we have high outdoor air temperature, which is the black line, the PCM to air heat exchanger is able to decrease the temperature of the air which is entering the PCM closer to the set point temperature, which for summer is 25 degrees, and while during the night it discharges and it goes closer to 20 degrees. So again, here we can see the comparison in outdoor curtain mode with a triple glazing unit, in which we can see that the heat losses during the night are comparable with a triple glazing unit with a natural ventilation. But again, we reduce the ventilation losses. So to conclude this presentation, we characterized the performance of this case study by defining some dynamic KPI for this innovative system, because the static one, let's say, were not enough. The double skin facade with all the ventilation strategy adopted and the PCM to air heat exchanger showed a very good behavior. But it's more efficient, the PCM to air heat exchanger is more efficient in winter period compared to the summer period. And the comparison with a triple glazing unit highlight the opportunities that this innovative system could bring to the building sector. We are still working on this test case, so we will continue with our test by also changing the melting temperature of the PCM and by continuing the analysis for a period like mid-season and summer, in which we need more data. So thank you for your attention.
Sorry.
Yeah, thank you, Ginevra. I think we can pass it to stage to Louena. Louena, can you hear us?
Good afternoon to all. Can you hear me?
Yes.
Yes, I will share my screen.
Yeah. During this time, you can post a question in the chat, and then the speaker can answer that also in the chat. Thank you.
You see my screen? Yes?
Yes.
Perfect.
Yes.
So I will try to make it a little bit lighter. So now we completely change the topic and we go into the acoustic characterizations from the material to the component to the room scale. So we'll check this, let's say, path of the entire characterization of materials up to the user. This image aims to show a little bit more about these invisible aspects that we have related to the sound. Sound is something that we feel like a positive aspect of our environment, even outdoor, indoor. However, we deal mostly with noises, and the main aim of the building skin is that of preventing this noise from the outdoor to get indoor or from other building environments into the environments of the user under investigation. So as you could see, there are different paths of the airborne sound as well as vibrations that could enter into the environment and become something that is negatively influencing the soundscape of the environment itself. There is some misunderstanding somehow between what is sound insulation, so what is the properties that we relate to the building elements and that are mainly aimed at attenuating sounds paths, and what is actually the sound and the quality of the sound within the environment. And this sound within the environment is mainly related to the properties of the acoustic materials within the environment, rather than on the layers and joints of the main environment, which becomes like the boundary between outdoor and indoor. Just to make this a little bit easier, what we name sound insulation is the attenuation of the transmitted sound from one side to the other side of the environment. And this is mainly does not affect the reflections within the environment, but just the component, the transmitted component. On the other side, what is sound absorption is a material that would reflect in a certain way and would somehow, let's say, compromise the reflections and the within the environment and not the transmission. So let's say that an absorbing material is not an insulating material and vice versa. And this is a common mistake that is seen also in very well peer-reviewed papers in the building environment sector. From the lab to the building scale, let's say that the complexity of the acoustic design goes in different stages, and it touches aspects related to the design variables up to the testing properties of the material at the material level, so in laboratory up to on-site measurements. Each of these stages, however, needs KPIs. And the problem with acoustics is that these KPIs, for example, in the building acoustics, are completely different for different environments. So it's not just the performance of the material and the component, but when you will test it on site, it will have to answer to these requirements. And as you could see, these are different names of the descriptors and also different numbers of the building element itself. If we talk about building facades, so exactly in the condition where the noise comes from the outdoor and goes into the indoor, also in this case, you could see that the different, let's say, nations, countries have their own characteristics. So one of the main goals of this cost action that you could see here cited was to harmonize these parameters, these descriptors and KPIs, as well as to check out the methodologies of the evaluation of these elements. On the other side, when we talk about room acoustics, so what is happening inside the environment, we usually talk about impulse responses, which is what you see on the left of the slide, which is composed of the direct sounds. So when you have a source and a receiver, and then all the reflections of the environment. So what we do with the materials is exactly combining and modifying these early and late reflections. So we have parameters for that. We have different parameters, but these depend on the use of the space. And there is also debate on what are the main parameters that could be the main descriptors, since we have energetic parameters, time-related parameters, and also spacious parameters. So it becomes something even more complex. As I mentioned, so to modify these impulse responses, we would need to modify and to design the properties of the layer that is somehow visible to the sound. And we modify through absorption, through reflection, and through diffusion. So let's see that the main categories of these materials properties are depicted in this image. So this means that we need methodologies to test all these properties and to see also if the existing methodologies actually are valid for the new materials and innovative materials. In particular, one of the main properties that is usually used to attenuate and to repress, for example, reverberation is the sound absorption. And in particular, the coefficients related to the sound absorption are mainly two, and these two depend on the type of method that is used to perform the measurement. So we have the normal incidence absorption coefficient and the random incidence absorption coefficient. So this will depend on the fact that we will we will evaluate the sample in a diffuse field, as you could see the scheme on the left, or in a normal incidence sound wave impinging on the sample. So we have the reverberation room method and the impedance tube method in these two cases that could be useful and can be used. What you see in this image is a new method that we have proposed for the reverberation room, which somehow scales down the size of the reverberation rooms, which are real rooms of more than 300 cubic meters, and which require a 12 square meter material, which means that at the design phase, it's impossible to have and would mean a lot of a higher cost of the testing. On the other side, we see that these methods of evaluation of the characteristics of the materials are quite useful to inform the digital tools that we already saw last week. So in that way, having validated measurement methods, and somehow validated simulations, this would help to have these loops that would somehow limit the evaluations in the large scale and more expensive ways of determining these properties. Particularly the absorption coefficient, as we mentioned, is measured in the impedance tube, but we can also measure it use the impedance tube for transmission loss measurements. In the first case, we measured the absorption coefficient, so the absorptive, the amount of energy that is absorbed by the sample. In the second case, we evaluate the amount of energy that is transmitted from our small sample. Usually, these two methods are used for common materials, like the ones that you see here, homogeneous with limited thickness, with the single-layered samples and so on. So what is now the trend is to challenge these methods. And we did this within the Iclimabuilt project by considering hybrid materials. These hybrid materials combine the properties of diffuse materials and the properties of absorptive materials. So we would see hard, irregular samples and over a core of foam, and which would act like a porous material. You could see that having big samples for the reverberation room method and testing also the samples in the small tubes that we use as the impedance tubes, the first question that could arise is which is the representative area of these samples? So this was one of the researches that we conducted together with Biogy3D, and in particular we also entered into more details into the methodology itself, so trying to understand if the method could be sensitive to the variations of this superficial let's say properties of the material. And in this case, the results were quite interesting, and let's say that they could challenge the existing methods, and there is more room for further validations on other materials. So these are 3 different materials, but we need also to test it further. Going back to the scale of the whole material, which is the hybrid material, then the test could go into the reverberation room, considering different configurations of the small samples that compose the entire panel, and testing also smaller and smaller samples to understand which is the sensitivity of the measurement itself. So as you could imagine, I mentioned that to do this in the real standardized measurement methods would require a 12 square meter material. In this case, we have a sample of 80 by 60 centimeters, which means that is a high reduction of the cost of the production of these materials, and as well as of the time dedicated to the measurement. On the other side, we said that these materials are hybrid, so here we test the sound absorption, but we need to test also the sound scattering properties. So the sound scattering properties would give us the amount of energy that is reflected in a non-specular way, so what is diffused by the material. These kind of properties are very difficult to measure and are not that much spread over the world, since, as you could imagine, from the scheme that we see here, you would need to measure in a stationary condition, which means no background noise, no variation of temperature and humidity, over a rotating table, that is what you see in here, in steps of 1 degree up to 5 degrees, which means that it's more than 2 hours of the measurement of rotations and continuous measurement of impulse responses in the vibration room. We could do this, and as you could see, we could do it in scale or in a scaled down sample of the same material that we saw before. So you see the combination of only the superficial elements, which are the ones that will interact with the sound, and the ones that would actually provide sound scattering. On the other side, looking at the transmission loss, the challenges that we pose to the measurement of the transmission loss in the impedance tube is how we could actually measure multi-layered samples. And this actually turns out that it's quite tricky and quite impossible to perform in an accurate way. So what we did in this case is, and which is the suggestion, is to provide the samples and to have really precise samples, and to have at least 2 typologies that could be somehow compared in order to have the KPIs and the comparison with a single variable that is varied. In our case, we had the common mortar and then mortar with an aerogel combined with it. So we wanted to check that if we change the density of this material, could it preserve its acoustic performance. So this turns out that doing the measurement with the sample and the precision that we ask to the sample construction, and having these leakages around the tube where the sample is mounted, could give us all these variations that you see here. This is the same typology of sample on the 6 samples that we saw before on the same material. So it means that we have a very large variability. Checking this variability towards the simulations, then it's a bit easier to understand which is the correct, the simulations with the, let's say, theoretical formulas that we have in literature, gives us the possibility to check which is the most accurate measurement that we could do. Let's say that the sample that we have, the TC that was where this mortar was part of, is a bit more complex, and you could see that there are different layers of this panel, and the only way to test it is within a laboratory, and then we passed from the small scale of the material scale measurement to the laboratory scale, and we go into the components. Also, this one is an untrivial condition, since these laboratories have to have these normalized rooms with desolidarized conditions, and this means that also the sample has to be mounted in a certain way. From this condition, we then go to the scale of the living lab, and then what we saw up to now, up to this point. So the component that we test in these laboratories could be tested also inside the living labs. The question is that are the living labs ready to host this kind of measurements? Since, as we mentioned, the possibility to measure these samples in the laboratory from the material up to the component condition through standardized methods would pose some challenges given the materials they are made of. So if we think about PCM plates, if we think about aerogel integrated in the layers, how would the joints behave, and how would we prevent the interaction between the samples that are mounted in the same living lab? So these are not trivial questions, and would need either a more, let's say, complex sensoristic, so measurement equipment, or at least would need some technological details that would allow us to do this. Let's say that the living lab are a very interesting point to start from the acoustic point of view, since they are not that much used in this direction. So if we look at the literature so far, it's a bit difficult to have the same, to have acoustic performances in terms of building acoustics, so sound insulation, but also in terms of objective room acoustic parameters within the environment. and to have somehow references and control over the environment. So as we saw in the initial slides, what we actually need to suppress in these living labs is the flanking transmission in order to have the direct transmission of each component. And obviously the next question is, are these components representative of what actually will be their application? So the risk is that let's say the joints and how these elements would be put in place in the building facades as building facades elements or in other conditions would somehow influence their performance. And as a rule of thumb, what we know so far from what are the common materials, they would lose at least 10 dB, which is quite a lot in terms of performance and KPIs. So to conclude, obviously we need to challenge the existing characterization methods that we have for the acoustic performance. We need to make them a bit more cost effective. So in order to use the same, let's say, possibilities to use the same samples in order to test different performances from the thermal to the acoustic, optical, and so on. Another issue, but this is not something that we can solve very easily, is the harmonization of the KPIs. As you saw, we have different KPIs for different countries, and searching for new methods and new protocols is obviously one of the main aim of the groups that are doing research on living labs and obviously also on innovative materials. And yeah, thank you.
Thank you, Louena. I think that's all for today. Sorry, it was a quite quite long, but I hope interesting seminar, and we were able to span really across many different scales and also domains of testing. If there is any question from the audience. So first of all, I thank all the speakers, and then if there is any question from the audience, you can let's say drop it in the chat, and eventually you find here all our contacts for further question in case you have.
Yeah, and I would like to share before we finish. Because now we are pretty late, sorry for that. But for the question, I think, yeah, you can have the contact with our speaker. And for now, do you see my screen, right? Hello?
Yes.
Yes, okay. So I would like to thank you all the speakers, and this is our next webinar, Iclimabuilt next webinar series, and the topic is innovative material solutions and testing for building envelopes, and it will be held on Tuesday, 11th of June. The time is between 10:30 to 12:30. And we have our invited speakers from different organizations and from different countries. And you will see this event. We will publish on LinkedIn and our social media tomorrow, and the registration will be open tomorrow. And please see or scan the QR code, and this is free of charge, of course. And please follow us on iclimabuilt.eu and our social media, LinkedIn, Facebook, and X. So thank you very much, everyone, for participating our webinar series. And I hope you have a nice day, the rest of the day. And yes, so I guess we can close our webinar.
Thank you.
Thank you, everyone.
Thank you, everyone.
Thank you.
Bye-bye.